Okay, for our next video, we're going to take a look at something a lot more complicated. In this case, we're still talking about Newton's law of universal gravitation, basically the thing that describes gravity everywhere in the universe. This time we're going to use it to explain something and find something that may affect you on a daily basis. So, for a lot of people, they get satellite television. Now, if this is the planet Earth, there is a satellite in orbit somewhere, usually very close to circular orbit. It depends on what type of orbit they're set up as. But if you're a fan of satellite television, so you've got a house and you've got a satellite dish off of it that points up into the sky. Now, one of the things you're going to notice about those, if you've paid close attention to them, is they always point to the south. Maybe not due south, but they're always in the south pointing direction. They're never pointed north. Okay? At least ones like this that are just fixed and stay in one spot. And we're going to get an understanding as to why that happens. What they're doing is they're pointed at a satellite in orbit above our equator, in a special type of orbit that is called a geo meaning Earth, stationary orbit. It's a very special type of something called a geosynchronous orbit, where synchronous means same time period, at the same time. Stationary, as you're probably somewhat familiar with the word, means it doesn't move. In this case, what's happening is, with the Earth rotating, as it does once every day, we have a satellite in orbit that the orbit takes exactly 1 day for it to go all the way around. So as the Earth turns a little bit, so if the satellite dish is pointed out this way, an hour later it's pointed this way, well, in that time, the satellite in orbit has moved here. Basically, it's a very special orbit that's set up that the thing does not appear to move very much at all in the sky. It takes 1 day to go all the way around the Earth, and the Earth spins all the way around in 1 day, and so it doesn't appear to move. Well, that's great, because then you don't have to put little motors on these satellite dishes so that they can point at the satellite that's actually beaming the signal to them. Okay. Well, this is a very special type of orbit. Maybe we could find out something about it. Well, if I take a look at my satellite, and I draw a free body diagram, I have a situation where the only force acting on it is the force of gravity from the planet Earth. And that's what's pulling it around in this orbit, in this circle. Okay, so that's a centripetal force, a center-finding or center-seeking force. It's the thing that's pulling that satellite around as it falls around the Earth. Okay, so we know that what's pulling on it is the force of gravity. We also know it's going in a circle, so we know that it's being subject to some type of centripetal force. And we know centripetal force is equal to our mass times our centripetal acceleration, which is equal to mass times our velocity squared over the radius of our circle. Well, I've got a circle here at some radius. I want to find out how far away that is so I know how high up, how far above the surface of the Earth to put my satellite so that I can get it to fall around the Earth here. Okay, so I know that I want my centripetal force to be gravity, so I'm going to set this equal to my force of gravity. Well, I know that my force of gravity, from the equation we're dealing with, is g times mass of the Earth, in this case times mass of the satellite, divided by the distance between them. Well, that's going to be here to the center of the Earth, squared. Well, that's that distance that I want, because I want to know how high up I need to put that satellite. Okay. Well, this is kind of a messy equation. Let me bring it down here so we can see it a bit better. We've got our mass times our velocity squared over our radius. That is from our centripetal force, because we know that this guy's moving in a circle, so there's got to be a force moving it in a circle. Okay, so it should satisfy this equation. The only force that's acting on it from our free body diagram is our force of gravity, and we know that that's equal to g times mass of the Earth times mass of the satellite. I apologize, this is actually the mass of our satellite, because that's the object we're talking about. Okay, divided by r squared. Well, r is what I want. Cool. I can already see that my mass falls out, so it doesn't really matter how massive the satellite is. That's cool. And I want to solve for r. Okay. Well, there's a problem. I know g, I can look up the mass of the Earth. I want to find r. Where am I going to get this velocity from? Well, okay, I know that I want it to do this big circle here, right? I want it to go this entire distance in how long? I want it to complete that in 1 day, so that it goes all the way around the Earth in the same time that the Earth spins underneath it. So, I know that the total time it takes, capital T, which we call a period, that's the total time something takes, is 24 hours. That's how long I want it to, or that's how long it has to go around this complete circle. I want it to be at exactly 24 hours. If it does it in 20 hours, then it's going too fast and it falls out of alignment where we don't see it sitting still in the sky. Or if it takes 30 hours, then it's moving too slow and then it moves off to the opposite direction. So I want it to take exactly 24 hours, and that comes up to 86,400 seconds when you convert it. Let me double check that. But as a good exercise, convert 24 hours to seconds, double check my work, make certain that I've got that right. But I know how long I want it to take to go around this. Now I need to know how long this circle is, basically the total distance it needs to go. Because I can say that my velocity is equal to my total distance divided by my time. Well, I know how long I want, or the time period involved, so all I need now is the distance I go. Well, this guy's a circle. There's some radius, I don't know it, but the total circumference here is going to be 2 pi r over t. 2 pi r is the circumference of a circle, so that's the total distance around this circle. I want it to do that entire circle in 24 hours, my t, my period, so I can plug those in. Well, this is my velocity. All right, that's the velocity I want. I can now plug that velocity in right here. And I end up with my velocity is going to be 2 pi r over t. I'm going to square that, divided by r, because I'm just plugging in my velocity there. There's my squared, so I'm squaring all of that. And divided by r equals g times mass of the Earth. The mass of the satellite fell out because I canceled it out over there, times r squared. All right, looking pretty good. I'm going to simplify this side a little bit so I can see it better. I'm going to draw that over here. I'm going to square the stuff, so I've got 4 pi squared r squared over t squared, and then that's divided by r, so I'm going to multiply by 1 over r to divide that. Well, that cancels out with the squared because that's r times r. One of the r's cancels out, and I'm left with g mass of the Earth divided by r squared over here. Going to multiply r squared on both sides, and I end up with 4 pi squared r cubed over period squared equals g times mass of the Earth. Those canceled out. Okay. I'm going to move my 4 pi squared, divide both sides by it, and then multiply by my period squared. But if I stop with just doing the 4 pi squared and divide that, get rid of that, and I end up with r cubed over period squared equals some constant. We'll talk about that in class, but this is actually Kepler's third law. It relates the semi-major axis, basically the radius of your orbit for roughly circular orbits, cubed, is proportional to our period squared. All right, so we managed to come across that here. And then finally, we're going to solve, multiply by t squared, get that moved over. Basically, I'm going to end up with, I've got some room over here, I'll end up with r cubed equals g times mass of the Earth times period squared over 4 pi squared. I plug in my values where g is 6.67 times 10 to the negative 11th. Mass of the Earth, as we've seen from previous videos, is 5.94 times 10 to the 24th. T squared, well, I know that t is 86,400 seconds, 86,400. And then 4 divided by pi squared. Okay, I can evaluate that. And I'll end up with r cubed equals some exceedingly large number. Did I write that down? Yes, I did. 4.50 E22. The units on this will be meters cubed. Go through and double check. I didn't keep them along with this, but that is something good to check to see if you've got the right answer. I take the cube root of both sides, and I end up with my R is going to equal about 42,200 kilometers. Now remember, that's above the center of the Earth, so if I subtract off my radius of the Earth, which is about 6,000 kilometers, then I'll end up with something very close to 36,000 kilometers. And if you check for the altitude of a geostationary orbit, you'll find that it is very close to 35,000 kilometers. Hopefully I'm not cutting that off too much. This is a very important number for anyone who likes satellite television, because that is where we need to park those satellites in orbit so that we can have nice, simple satellite dishes that don't need fancy motors to point off at different types of satellites. Okay? So, it's a little bit messy, but it uses our universal gravitation. It also uses some of the uniform circular motion material that we've talked about. And we've applied some of the other things that we know. We're going to deal with period and angular velocities, which is another way of looking at this. We're going to deal with that more down the road when we deal with rotational mechanics. But here we've gone through and we've actually derived how far away we need to put that satellite.